Okay. Okay, I'm going to record too. Robert, can we record your
You can
presentation?
record. Yeah, you can. Yeah.
Okay. 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 Let us start. We are very pleased and very honored to have Professor Robert Niven to this seminar, this series of seminars. And as Dr. Lee Wang is going to make a short presentation of Professor Robert Niven, and then give you the time for the presentation. Lee?
Yes.
Can you?
Okay.
Yes.
Well, yeah, thank you.
Go ahead for the...
Today, we are very pleased to have Professor Robert Niven here to give us a talk about his work. Professor Robert Niven is an professor at University of New South Wales in Canberra, Australia, and his research interests include probabilistic inference, theoretical fluid mechanics, and environmental contaminants. And today he will present a work on Bayesian inference for construction of inverse model from data. So Professor, please, you can start your presentation now.
Okay, thank you very much for a very nice introduction, and it's an honor to be here and presenting to this community. So as mentioned, I'm going to talk about Bayesian inference for construction of inverse models from data. And first of all, I'm just acknowledging a number of my collaborators and students over several years and funding. So what I'm going to talk about today, first of all, why Bayes? So why do we do this? What's important? So I'm going to talk about inverse problems and methods of inference. And in fact, I'll go right back to the meaning of probability because that's necessary to understand some of the motivation here. Then I'm going to talk about Bayesian framework for model identification, which is going to include a discussion of regularization methods and some advantages of the Bayesian approach. And then I'm going to examine a number of different example systems, including dynamical systems, rainfall runoff systems in hydrology, and also I'm going to consider a problem of groundwater vulnerability, and then some conclusions. So first of all, why Bayes? So if you look at this slide here, so we have a situation where we have a model, some kind of physical model which is generating data. And so there are two types of inference problems. The forward problem is we're using the model to generate the data. And generally that's a trivial exercise. Generally that's what's happening. But there's also an inverse problem, as we call it, to use the data to infer the model that is generating the data. And this is generally much harder. So if we discuss a number of different inverse methods, so first of all, there are deterministic methods in which we put together the theory and the data. We have some sort of fitting method, like a regression method or something like this, and we derive a model. And the disadvantage of this approach, hence the name deterministic, is we only get one model. We might get some kind of error bars or some other indication of uncertainty, but commonly not. We just get one model. The second type of approach is the methods developed in orthodox statistics, where we put together the theory and the data, we undergo a hypothesis test, we have to choose between two hypotheses, and as represented in this diagram, there's sort of a space in a basically a probabilistic distribution where we either reject a hypothesis or do not reject the hypothesis. If you actually spend some time looking at this approach, it's a very strange way of formulating this problem. We can only ever reject a hypothesis. We can't accept a hypothesis. And it only ever gives indirect measures of uncertainty of your model. So things like levels of significance, confidence intervals, p-values, and so on. There's a number of data-driven methods that are very popular now in the literature, particularly based on neural networks and so forth. But once again, first of all, they're difficult to incorporate theory. So they really are data-driven, which implies that quite possibly we haven't even considered the theory. They tend to be described as black box methods with little insight into their meaning. And again, we only obtain one model. And so generally we don't get any estimate of the uncertainty in the model. And finally, Bayesian inference. So here we put together, so the top group of pictures is for a discrete distribution, or underneath is for a continuous distribution. So we put together our prior knowledge and our data using this process, which we're calling the Bayesian update. And then we end up with probabilities assigned to different models. And we can do that in a discrete space or a continuous space. So we're combining the theory and the data in order to get the probabilities of models in a model space. And when you think about it, this is a really natural way of representing how we should be doing inference. And a further advantage is we can go back from our inferred distribution, the posterior, we can go back, import that in as a prior and update that with new data, and we can keep going around and around. So we can continually update with new data. Okay, so there's the different methods of inference. And I also wanted to mention briefly about the meanings, different meanings of probability. And so first of all, from the classical period, so this is a very long time ago, starting from Cardano in Italy, where probability was defined as the number of outcomes of interest over the total number of outcomes. And this is a very natural definition when you're gambling. And so, for example, a toss of a six-sided die, we would assume that the probability is 1 on 6 of each side. And similarly, the toss of a coin, 1 on a half, is a probability assignment. So that's a classical definition. I'm putting these a little bit out of historical sequence. In the early 20th century, there is a group of researchers listed here and many others, and they defined a probability as a measurable frequency for an infinite number of repetitions of a random experiment. And so I'm going to refer to these as the frequentist school of probabilities, that probabilities have to be measurable, they're a measurable frequency. And it's this thinking, this philosophy, which gives this field of orthodox statistics with a whole lot of different components. But we can criticize this on many grounds. First of all, it only allows a probability to be a measurable frequency. But there are many situations which we don't have that. So what if we have a limited data set? So we don't actually have a population from which we're supposed to be drawing. What if our population is changing in time? What if we're really just trying to assign values to degrees of belief in our proposition? And so based on all these criticisms, we can argue that this frequentist definition is too narrow. So that brings me to the third school, which was actually the second in historical development, the Bayesian, or the plausibility school, I'm going to call it, in which a probability is, we can describe it as a plausibility. So it's an assigned degree of belief based on what we know. So it does not have to correspond to a measurable frequency, and we're assigning it due to ignorance. If we're not ignorant, if we know something, we don't need probabilities. So the probabilities are only useful if we don't know something, and that's their purpose. And so we can describe this approach as being subjective. Many people have, but it's rational. So what I mean by that is that if we have different observers with the same information, they should make the same probability assignments, so the same degrees of belief. But alternatively, if observers have different information, then they quite possibly will make different probability assignments. Probabilities are not measurable frequencies. They're an assignment based on what you know. If the information that you have changes, the assigned probabilities will also change. And there's a school of mathematics called plausible reasoning, which again, a number of researchers have worked in this field, Pollier, Cox, and James in particular. And they've proven that these plausibilities are unique. and they obey the sum and product rules of probability theory. And so, in other words, we can use plausibilities as our probabilities. And so we don't have to adopt the frequentist definition. We can have a plausibility definition of probabilities. And that's quite fundamental. Okay, so as a result of this, we come up with Bayes' theorem. And this is based on a very simple product rule, which we can derive using the sum and product rules of probability theory. So here it is here. And these D and H could be any two different propositions, but we're going to make a particular definition where D represents data and H is the hypothesis. And we can rearrange this equation in this form. And so what we've got now is a probability of a hypothesis given a data is equal to a product of these terms. This first one is called the prior probability. This one on the numerator is called the likelihood. So it's the probability of the data given the hypothesis. And in the denominator, we have this term, which is called the evidence, the probability of the data. And what we're noting here is that we're defining a probability of a hypothesis given the data. It's not a measurable frequency. It's an assignment based on what we know. And that's the essence of Bayes' theorem and the use of Bayesian inference. There are some other forms of this. So if we have a set of mutually exclusive hypotheses, a discrete set, we can write down Bayes' rule for that. Similarly, if we have continuous data and continuous hypotheses, we can represent them with different parameters, x and theta, and we can write down a continuous form of Bayes' rule like this. So if we consider statistical methods as they have been developed over the last 100 years, we have a group of methods, which I'm going to call orthodox statistics. And on the right-hand side, there's Bayesian inference. And it can be shown, and this can be shown mathematically, that these orthodox methods are correct only to the extent they're consistent with Bayes' rule. Otherwise, they're wrong. And there are many examples in which it has been shown that the orthodox methods are wrong or lead to incorrect conclusions. So the question really is, well, why do we use these methods? Why don't we just directly use Bayes' rule? And that's what I'm going to demonstrate today. There's a hierarchy of different Bayesian methods. And I must sincerely thank Ali for making me aware of this sort of hierarchy. So first of all, there's the Bayesian maximum a posteriori estimate. So what this does is it gives you assess the maximum value of your posterior that you calculate with Bayes' rule. And so it gives you a single value, and you can use this as your estimate. And so that enables you to choose a model. It may not be the best choice, but it gives you a method to choose a model. Secondly, you can undertake uncertainty quantification. So you can use the posterior that you derived in order to give you some statistical properties. So, for example, the variance of the posterior can give you uncertainties in your model. Thirdly, taking this to a much more complicated calculation, you can do functional predictions, so you can fit functions to data. And finally, you can undertake an exploratory Bayes approach where you explore the shape of your posterior distribution. And that leads to different methods, MCMC and nested sampling. Now, today I'm only going to talk about the first two of these, and I'm not going to get into the third and the fourth categories. And you'll see why I do that in a minute. So let's just look at some existing methods for model identification. And so what I have here is just a simple model representation where we have some dependent parameters y are a function of some independent variables x, and f is what I'm going to refer to as the model. And the examples I'm going to talk about shortly are dynamical systems, rainfall runoff systems, and groundwater pollution. And so in all of these cases, we're interested in trying to derive this model f. And so we have an inverse problem. So we're trying to infer that F from data, so we can call that model identification. If we know the function class of the model, or we assume the function class, then we can simplify that problem to one of parameter identification. And that's what I'll be doing. And so the discretization purposes, we may, for example, have time series data, or we may have spatial data. I've represented this with time series data with, so functions of time t, but they could similarly be functions of a spatial variable, in which case I'll change the symbol and it'll be a symbol x. So what you can see on the left-hand side is we have a capital X. This is our time series, or it might be spatial series. And then I've sort of stacked the time series vertically to make a vector. If there's a multi-dimensional data, then you end up with a matrix of data, which is shown there. So there's an n by n matrix. Similarly, for the dependent variable, we do the same thing. Then what we do is we choose an alphabet of functions that we're going to apply to the data. And that gives us this large matrix theta. And you can see in this particular example, the functions, there's just a one function. There's also functions that are derived as polynomials of the parameters that are used in the data. And in this example also, we've got some trig functions as well. And so what we're interested in doing is writing out this functional form. So we now have a discretized functional form of our system where we have our functions applied to the data in this theta here. We have our dependent variable y on the left-hand side. And so the theta is multiplied by some either a vector or a matrix of coefficients, and we're trying to determine the values of those coefficients psi. So we're trying to invert this equation to find psi. And commonly this is conducted with a regularization method. And so first of all, we could use, to invert this equation, we could use least squares regression. And so this is how we would write this. So we have our estimated value of the psi coefficients is given by the minimum of this objective function. And this objective function here is just defined by the residual, as you can see, which is in which this notation is representing the L2 norm. So the square of the L2 norm. And hence, that's why it's least squares regression. If we're dealing with matrix quantities rather than vectors, then we can just apply this column-wise. So that's our least squares regression problem. But in practice, what we have is we have some noise in the data, and this can cause some computational difficulties for this regression procedure. And so what we generally do is add another term, which I'm going to describe as a regularization term. So that's this term over here. And the purpose of that is to try and reduce the effect of the noise. And there are many different regularization methods, as you can see here. So this regularization term, we can take a zero norm. There have been one norms. There's thresholds that have been used. There's this form here, where we have a regularization matrix. Some people have used bilinear forms, so norms defined by bilinear form, which we'll do shortly. And you can also do a constrained optimization with some constraints. And there are many connections between these methods and other methods that are used for matrix decomposition, which are very popular, and also with Koopman analysis for basically extrapolating from an observable. So there are many different methods, but this leads to some concerns. The choice of the regularization method does appear ad hoc. It doesn't appear to be very rigorous. Secondly, if we're using a method that has a regularization coefficient lambda, this coefficient is often chosen arbitrarily or by some heuristic method. There's a limited or no ability to judge the validity of a model. So once you've got your model, you can't go any further. You just obtain a model. And similarly, you can't compare different models. And you can't take it any further in terms of trying to assess the uncertainty in your model. So these are some limitations of the traditional regularization methods, and that's why I'm going to explore and demonstrate the Bayesian method. So here's a Bayesian framework for inverse problems. So we start off with our original statement where our dependent variable is a function of an alphabet of the independent variables multiplied by a vector or matrix of coefficients psi with noise epsilon. And then we represent this in a probabilistic form. So this is Bayes' rule. So this is the probability of our model given the data. And that's given by the Bayes expansion in terms of a likelihood, a prior, and an evidence. And if we just do this, if we're only looking for the maximum of this function, we don't need the denominator, so we can just establish proportionality like this. And so the map, or the maximum a posteriori estimate of our posterior, is given by this. You'll notice that I'm using logs of probabilities. That gives us better resolution, and also there's some mathematical reasons for doing that. And so we're trying to maximize the log of our posterior in order to pick out the posterior that has the maximum value. And then when we substitute in here for our posterior in terms of our likelihood and prior, we get this expansion. Then we can make a very simple assumption, is to assume Gaussian noise and a Gaussian prior. And we can write down those Gaussian functions. These are multi-dimensional Gaussian functions. And you may not have seen this notation. This is a notation using this bilinear form that I discussed earlier. And if you're familiar with multivariate Gaussians, you'll see that this is correct. What we've done, though, is we've lost the denominators from those Gaussian functions. We're only seeking a maximum, so we no longer need those denominators. So here's the likelihood, here's the prior. And so what we end up with is we end up with this functional form. And because there's a negative in here, we can make an inversion between maximum and minimum. And so we've now got the argument of the minimum of this function, where we have a likelihood term and a prior term. And you'll notice this looks like our regularization method that we just discussed. And this, in fact, gives us a rational justification of a regularization method. We can take it a little bit further. When we have isotropic variances, so in other words, we have our covariance matrices with diagonal terms that are all the same and then no covariance structure at all, just variances, and we make those substitutions, what we end up here is a likelihood and prior become two norms. We make a substitution and we get this function here, and we can rearrange it in this form. And so this is giving us directly our regularization method that we saw earlier. And so the Bayesian map is not only giving us this two-norm regularization with a regularization term, it's also giving us the value of the lambda that we should choose in order to do that calculation. So that's very powerful. Okay, so that's the simplification. Furthermore, even if we don't make the simplification, we have access to an analytical solution. And so if we have a Gaussian likelihood and a prior, it is known that the posterior will also be a Gaussian and has this form. And so our estimated value of our coefficients is given by this, and our estimated value of our variance is given by this. Our covariance matrix is given by this. Sorry, instead of x dot, there should be a y in here. So we now have a functional way of making these calculations. We can do these matrix inversions in MATLAB. It's feasible for small data set, reasonably small data sets. We can extract our coefficients, and we can also extract from this covariance structure, we can extract the diagonal terms and get standard variances or standard deviations in our model parameters. We can take it a little bit further here as well. These covariances of our likelihood and pri are not known in advance, and so we can incorporate them into a joint Bayesian inference, so with a joint posterior. So this is what it looks like, and with some simplifying assumptions that are quite reasonable, we can effect a separation of terms like this. There are two methods that are commonly being used to analyze these functions. There's a JMAP method where we just seek this maximum here, and we use the analytical solution that we just, discussed. Alternatively, we can undertake a variable Bayesian approximation where we assume separation of these quantities, and we use a Kullback-Leibler criterion in order to do an optimization. And again, for our Gaussian likelihood and pri, we can use the analytical solution that we know, and we can also use inverse gamma distributions for these other quantities in order to do that estimation. Okay, so that's the theory. That's the apparatus. So what are the advantages before we go and consider some examples? So first of all, we've seen the Bayesian map framework. It gives a rational justification for regularization methods. So the residual comes through as the likelihood, and the regularization term comes through as the prior. And for that isotropic situation that I discussed, we also get directly the regularization coefficient. We can, if we want to, though, we can access the full Bayesian apparatus. And so we've got our coefficients. We can also undertake uncertainty quantification in our coefficients. And if we wanted to, we can take it further than I'm going to today and explore the shape of that posterior. We can thirdly, estimate nuisance parameters. And fourthly, it has been shown that this inverse problem is well posed, and so it will give a valid solution. Okay, so let's look at some examples. So some examples first of some dynamical systems. Now, I'm pretty sure that most of you in any branch of data analysis or mathematics will have seen this system. This is the Lorenz system. It's a famous chaotic system where you have movement of basically movement through a coordinate space around this is called the strange attractor. So there are two locations at which this moves around, and then there's sort of like a swapping around of this orbit. Seemingly, it seems to be arbitrary, even though it is deterministic. Now, what I've done to analyze this system is I've added Gaussian noise. So you can see that this is a noisy system. And so can this Bayesian apparatus handle this system? That's the question. So now I've applied here two different methods. So first of all, there's a Cindy method. So this is a traditional regularization method using a threshold, which is one of the methods I had in the table that I discussed earlier. The Cindy method works very well. And so what I've got here on the left, these are plots of, these are the correct values of these coefficients in the psi. So correct the true values minus the estimated values. And you can see these are very small numbers. These should all be very close to zero. And in fact, they are very close to zero. So we're getting very good estimates of the coefficients from our time series. And when we reproduce our time series, so here's our noisy data, here's our estimated time series. Whoops. And this plot here is the difference between these two. You can see we're able to predict this time series extremely well up to some point. At that point, what's happening is we're reaching the limits of numerical precision of our computer, and we're not able to calculate our coefficients precisely enough to reproduce that time series for all time. And so at some point, our prediction will break, and then we'll have some deviation. But nonetheless, we're able to predict those coefficients extremely well over a time interval of the time series. So that's the Cindy method. If we now apply a Bayesian method using the JMAP algorithm, the performance is much the same. So here's our noisy data, here's our estimated data. We're predicting our time series very well to a similar kind of transition point. But if you look on the left-hand side, what have we got here is we've got estimated values of the coefficients, but these have been subtracted from the true values. So all of these should be 0. But on top of this, we have error bars. So what we've done is we've used the predicted covariance matrix of the posterior and extracted the values of the standard deviations from that matrix and then plotted these. And so what we've got is we now have estimates of the uncertainty in our model, which is something that the previous method is not able to do. So that's a really powerful advantage of this method, is we're able to do uncertainty quantification as well as predicting values of coefficients, we can predict the errors in those values. If we apply the VBA method, we have a similar pattern of results. The results are very similar. They're not identical, but they're very similar, and we're also able to reproduce that time series. Okay. In terms of the behavior with iterations, so the way that we have conducted these analyses is we've iterated over a convergence parameter. So for the Cindy method, the threshold lambda is our convergence parameter. And for the Bayesian methods, we have this ratio of parameters. It's a b divided by a minus 1. These are parameters that were used in the inverse gamma model that we've used for those two different covariances, and we've iterated. So the iteration procedure starts on the right-hand side and moves towards the left in all of these cases. You can see the convergence in the Cindy method is very rapid. These two methods, they converge down, and if I go to my next slide, the red circled points are the points that we choose as being a converged time series and a converged analysis. And if we just make a comparison here, if we push this algorithm further, what happens is we get some numerical error. We start to get predicted values that are different to the actual value. So we're getting some deviation from the 0, whereas these should all be lined up with 0. So what's happening here is we're reaching the computational limits of whatever machine that we're using for our calculations. So we're going to use this break in the slope in order to choose our predicted values in each case. So that's the Lorenz system. Now I'm going to talk about a few other systems. So there's this strange system, which is, those of you, again, familiar with dynamical systems will be familiar with biological population systems, predator-prey systems in particular. This one is a 3-species system with 1 predator and 2 prey. And so there it is there. So it's represented by a polynomial with a 1-term, linear terms, and quadratic terms multiplied by some coefficients. Not all of these coefficients are realized, so there's quite a few zeros you can see here in this matrix. This is what the system looks like. It has it sort of orbits around and it can move between these different pathways. Again, I've added Gaussian noise in order to make this inference more difficult for myself. So we do the same thing. We use the traditional method, the Cindy method. We're able to recover values of coefficients to very low values, and we're able to recover this time series. And in this case, we're able to recover the time series across the entire window of time that we considered. So that's very nice. If we apply the JMAP method, what we get here, there's a couple of differences. We don't quite reproduce the time series over the same threshold or to the same time interval. But what we do get is we get values of coefficients and we get error bars around those values. So again, we're using the Bayesian posterior to give us those standard deviations of our predicted coefficients. The VBA method gives a similar result as well. And to look at these plots of the convergence of these algorithms, so the Vance system with Cindy, again, you have a sharp transition to a converged value. And similarly to what we saw with the Lorenz, both the JMAP and the VBA, they sort of march downwards and then they reach a converged value. Okay, our third example, and this is a very strange one. This is called the Chua system. And this contains an alphabet of functions which are linear values and also shifted absolute values of those linear values, which is quite unusual. And again, not all of these are populated in this matrix, so there's quite a few zeros here. And it has been shown that this system is chaotic under certain parameter specifications, and here it is here. So again, it looks like a strange attractor, but it's more or less, it's very flat. It's just sort of sitting almost in one plane in a three-dimensional space. I've added noise again to make the inference more difficult. And here, what we get some interesting effects here. So when we apply Cindy, we have rapid convergence. When we have JMAP, we have a similar behavior to what we saw earlier. But when we apply VBA, for some reason, we get an iteration over some completely different solutions. And so it doesn't really properly achieve convergence, which is interesting. And now, why is that? Let's look at what happens. So for Cindy and for JMAP, we're able to reproduce our time series very well up to for a time interval. So they reproduce the time series fairly well, but in both cases, they don't actually find, neither algorithm finds the original coefficients. Now, why is that? What the algorithm has done is it's found an alternative solution. If we go back to our specification of the system, you'll notice that if you have large values of y, then whether the variation appears in this y parameter or in the shifted absolute values, according to the algorithm, it doesn't matter. And so what it does is it actually puts some uncertainty into the shifted y values instead of into y. So what it's done is it's actually found an alternative solution to this problem. And so I agree, this is a very strange problem. It's a problem in which there's uncertainty. There's a possibility of finding multiple solutions. And in fact, it leads to a very deep question. When you're conducting inference, what do we mean by the correct model? Does it have to be the model that generated the data? Or can it be an equivalent model? And in which case, how do we make judgments about correctness? So I'll leave that as an open question. I'm not going to talk about that very much, but it does open this to some interesting discussion. Okay, so there are some dynamical systems. Now I'm going to talk about some hydrological systems. My background, I should say, is in engineering, particularly civil engineering. And so I'm interested in many problems to do with groundwater flow or water catchments. And so this first example is a rainfall runoff analysis. And maybe you haven't considered this problem before, but we have rain. So rain falls on a water catchment and then seeps through the soil and unconfined aquifers and eventually reaches streams and then causes stream flow. And so there's a correlation between rainfall and stream flow, which is very important for hydrologists to understand. So we're looking for the transfer function or the response function between rainfall and stream flow. Okay, now how is this done up to date? So the traditional method is called, and makes use of this thing called the unit hydrograph. And so the unit hydrograph is the runoff, the runoff distribution resulting from a unit depth. In most countries, that's a 1 centimeter depth of rainfall excess, which falls during a given storm duration. And so what is done is there's a correlation that's established between this first graph here. The hiato graph is the rainfall data. The second graph is this is the unit hydrograph, and that is used to construct the stream response, the runoff distribution with stepping of time, with a sort of a time interval, and it's making use of many assumptions, including a principle of superposition. So essentially, it's making an assumption that that catchment will respond to rainfall in exactly the same way, regardless of the history of the rainfall. And when you think about that, that doesn't make sense. But this is the standard method. So what I'm going to do is formulate this problem this way. And so Q is the stream flow. So this is the flow in a stream or a river. P is the precipitation. So this is the rainfall. But I'm going to use a staggered matrix like this because we're considering time histories of rainfall, and there could be a delay in the response of the stream to the rain. And so we need to allow for that delay. So that's why it has this strange shape. We have our vector of coefficients here, psi. We have another quantity called the base flow, and this is in hydrology. Hydrologists consider that there's sort of like a minimum flow in a stream, and that will be flowing all the time, and so they will subtract that from their stream flow in order to do their calculations. So I've included that in this analysis here, and then there's also an error term here. Now what we want to do is we want to put in our data, we want to invert this model to find psi, so to find the value of these coefficients, and then we can use this instead of using this unit hydrograph. Let's start with a textbook example. So this is from a textbook in hydrology. Rainfall data are often represented in an upside down graph. So this is the rainfall. So there's a rainfall that happens on this catchment, and then there's a response of the catchment. And so this is the stream flow. It's a beautiful curve there, an almost Gaussian curve. And when we go through our Bayesian analysis, here are our true values of our coefficients. Here are our predicted coefficients. We subtract the two. We end up with error bars on our coefficients in exactly the same way that we've shown earlier. And in terms of our prediction, so this is our true stream flow. This is our predicted stream flow. They're very close. There's an error, which is a very small error. So for a textbook example, this works very nicely. And that demonstrates this idea of the unit hydrograph. But let's look at a real example. Now, this is an example of a water catchment. It's not actually very far from me. So I'm sitting in here in Canberra in Australia. And so this is a water catchment, basically the Queanbeyan River in Tinderry in New South Wales. And these slides here are showing I've extracted data from different databases. There are Australian government databases where you can extract stream flow information and rainfall information. So I've got that information and put that together and extracted just an episode. So just an episode of, so this is rainfall here, and this is the response. This is stream flow. But what you can see, and this makes sense, when it rains, it doesn't rain evenly. Quite often you have rainfall in a very strange pattern like this. And that's a real life example. And there's a stream response. Now, we don't know what the transfer function is, so I can't report the true values. I can't judge the true values. But what I can do is report these are the predicted values of the coefficients. So these are basically steps in time. So this is the response of that stream in time to this rainfall pattern. And we can also infer standard deviations, so uncertainties of these coefficients. And when we plot our stream flow and our predicted stream flow, they're not identical, but our prediction is actually very good. And especially given the fact we're using some raw data that are very strange data here. So finally, an example of groundwater vulnerability. So, and this has been led by my PhD student, Nazrin Tagavi, who's here in the audience, and you can ask her many questions about this work. So the formulation here is, so we're interested here in concentrations of groundwater pollutants. So groundwater is the water that's in the ground, it's flowing in the soil or in underground aquifers, and it becomes polluted, particularly in agricultural areas, it becomes polluted by nitrate. And so what we're interested in is establishing what is the correlation between these nitrate concentrations and the major hydrological variables of that system. And so what we do is, well, what we want to do is establish this correlation and get these values of these coefficients psi. And we have to do that at the locations at which pollutant data are available. But then, having got this solved our inverse problem and got our matrix psi, we can then use that to construct a groundwater vulnerability map for the entire water catchment, even at locations at which the nitrate has not been measured. So we're able to actually, it's basically a risk map or a vulnerability map of what is the likely nitrate concentration throughout an entire aquifer. And this can be done within a geographical information system, which is a very nice environment. And so we're handling spatial data in a very natural way. So the study area that we chose is the Burdekin Basin, which is a large water catchment in Queensland. That's one of the states of Australia. So there's the Burdekin Basin there. It's the second largest water catchment in Queensland, and there's significant agricultural activities in that catchment, particularly sugarcane, but also some cattle as well. And there's concerns over pollutant impacts on wetlands in that area, and also impacts more broadly to the Great Barrier Reef, which is a large coral reef offshore from Queensland. And here I'm just acknowledging a number of people who've made a contribution to this work in terms of providing data or giving us information about this catchment. And so what Nazrin did was collected raw data for a number of different hydrological parameters. So here they are here. You can see there's a lot of different things that we could consider as variables. And so some of these probably more strictly you would call meteorological parameters. Some relate to the soil, some relate to the rock, and some relate to the surface expression, so the topography. So there they are. So there's the parameters that we're interested in. And again, you can see this is done in the geospatial environment. And so we're able to handle this data in that way. So the traditional method for assessing groundwater vulnerability is to calculate a vulnerability index. And this is a linear function of 7 parameters based on pre-specified weights and assigned rates. So the W is the weight. So these are fixed values that are part of this formula. And then to each of these variables, so these are these hydrological variables here, we assign rates. So what we do is we take the raw value of each of those variables and convert them into an ordinal value, which we call a rate, in order to do this calculation. And so here are these variables. And so for various reasons, these are called the drastic variables, you can see, because D is depth of groundwater, R is recharge, and so forth. So we have the drastic variables, and this is known as the drastic method. Okay, so we can apply the drastic method and apply that to our aquifer system, to our water catchment. And these are the predicted groundwater vulnerabilities over the catchment. And we've used a graded scale here from very low to very high vulnerability with color mapping here. And so this analysis identifies certain regions as being highly vulnerable to groundwater pollution. The trouble is, even though this is a traditional method, it's the most common method used around the world for groundwater vulnerability assessment, when we compare these predicted values of vulnerability to the nitrate concentration, we end up with a very poor correlation. So 0.07 as the Pearson correlation coefficient. We can improve this a little bit by adding a land use parameter. There are land use categories that can be assigned across this water catchment. And this information is available from the Australian government in a database. So we can go through the calculations and assemble what we call the drastic L approach with an extra parameter for the land use. And that gives us an improved correlation, but it's still 0.2. It's not a very strong correlation. Okay, so that leads us then to a Bayesian approach, is to calculate the coefficients in that formulation that we saw earlier by Bayesian regularization with the nitrate data. And here's the analysis here. The approach is much the same. We've conducted iterations over this ratio of parameters here. We've chosen some converged values of this distribution. We've extracted our values of our coefficients. And you can see here, there's a plot of the measured nitrate concentrations and the estimated. There's still a lot of difference between those two, but we have an improved correlation. So our correlation coefficient is now 0.39, which is a stronger correlation between those parameters and the observed nitrate data. And when we actually then apply that correlation over the entire catchment, so now we're making inference at locations where there's no measured nitrate concentration. So this is an inference map of vulnerability. This is hot off the press. In fact, Niven has just given me this picture just a few days ago. So thanks very much for such hard work in getting this together. There's a couple of things to point out. You'll notice that the distribution of vulnerabilities now has a skewed distribution. So it's very different to what we saw earlier with the drastic method. And secondly, the locations where we are now predicting high vulnerability, they're quite different in this analysis compared to that earlier analysis. So we have a very different assessment, particularly of these zones of high and very high vulnerability to nitrate. And that's important because that will help users in those locations in order to make judgments about protection of the environment, fertilizer use, groundwater use, and so forth. And we can make some further comparisons. So here's a table here with these R values and also a couple of other indices. So we have the drastic and the drastic L methods. We've used the Cindy method as our representative method of a traditional regularization method, and we've got the JMAP and VBA, and you can see there are quite some differences. In fact, the Cindy method did find this solution as well, but we have various other reasons for using Bayes. There's also what we also have just done is a sensitivity analysis on the choices of the parameters and the type of parameters that have been used as well. Okay, so this brings me to my conclusions. So we've looked at Bayesian inference from data. So inverse method, we can calculate probabilities of models within a model space. And for this reason, Bayesian inference offers many advantages over traditional methods of solving inverse problems. Secondly, we've looked at the Bayesian maximum a posteriori method, the MAP method. This gives a rational justification for regularization methods, with the residual is associated with the likelihood and the regularization term is associated with the prior. And this actually leads to different methods. So if we have non-Gaussian functions, then we can implement those, and we have an apparatus for doing that. It'll be harder to solve, but we have a mathematically sound method for doing that. Thirdly, if we wanted to, we can access the full Bayesian apparatus. We can do uncertainty quantification in the model coefficients. We can estimate nuisance parameters. We've done both of those. And then if what I haven't demonstrated but can be done is we can explore the posterior. That's the output of the Bayesian inference. And finally, I've demonstrated this by a number of applications. We've looked at a number of different dynamical systems, including a strange one. We've looked at rainfall runoff systems in hydrology, and we've also examined groundwater vulnerability assessment. So that's what I wanted to talk about today, and thank you very much.
Okay, thank you very much, Robert. It was very interesting, and in particular, the different application area was very interesting for me to see how these methods can be applied in different area that I didn't know too much. Okay, so I will have a few questions and suggestions, but first let's see if in the audience there are some questions or comments. Everybody here? Yes.
I have
Please.
two questions. The first is when you estimate the parameters in Kasi, it's called Kasi, right? So first of all, a model should be should be decided. For example, in the first case you use like the polynomial model, and in some cases you used, for example, in the last application of vulnerability model, you used there is a huge model with many variables, and for example, in polynomial models, you choose different kind of polynomial models. So is there a strategy to fix the model, or for example, the order of the polynomial model, or the formulate of the model?
Yes, no, that's a very good question. And that's, in fact, that's one of our most important questions. And I can give you an answer. I mean, one thing that we can do is we can run this inference multiple times with different choices of our alphabet, and that will give us different functions. And then, but then what we have to do is we have to compare the predictions from different models. And that is a difficult thing. There are some indices that have been used. For example, there's a Bayesian information criteria, which is used for this purpose. And so that can be used. What that does, I don't actually have a slide of that here. I should have anticipated your question, but that the formula for the BIC will contain not just it'll contain the likelihood, and it will contain the number of parameters that are used in the model and the number of data points as inputs into that calculation. So what it's doing is it's going to penalize models that have too many different variables or parameters. And so you can use this kind of thing to try and choose simpler models, because obviously a simpler model should have less terms. A quadratic model is better than a third order model. A linear model is better than a quadratic model, and so on. But I do agree with you. This is actually a very deep question, how to choose a model. And we saw one example here where we had a model with absolute values in the model, and no one would guess that. I mean, it's beyond comprehension that anybody would think about that and use absolute values in their choice of an alphabet, but that's what was used to generate that model. So it's just an interesting example of something that is a little bit strange. I have got into some other work with some other models where if you have reciprocal functions, and particularly if you have reciprocals of parameters and like reciprocals of functions of parameters, you can get into this very difficult situation where you would never be able to guess what the model is. And if that's the case, then you have this big question about what is a good model. Is the model discoverable from the data? So can you discover the model at all? Or can you, is the best that you can do is to try and fit it with some function and hope that that works? So I don't think I've given you a very complete answer, but that's because this is actually a very deep question, and it's a very important question. And in these situations, mostly we've known what the model is or the model function is, but in cases where we don't, we have to infer that as well.
Mhm.
So thanks for the question.
Yeah, I think that
Mm.
I had also the same question. If you put the slide number 29, we can discuss a little more about
29, yes.
this one. Yeah, exactly. The choice of the alphabet. Can we add some more terms? Can we delete some of these terms? And
Yeah.
how
Yeah.
did we choose? Did you choose this alphabet actually?
Yeah, that's a good question. I mean, one way you could do it is just to approach it sequentially with a simple model. Choose a one. That doesn't work.
And
Choose linear. That doesn't work. That's not going to work for this system. So then you're led naturally to quadratic. If you add third order polynomials, and I have done this, then you don't get better predictive capability. And in fact, you find from that analysis that the third order terms are not important and so can be excluded. So for this system, it's actually well behaved enough that you can exclude the third order terms. But there are some chaotic dynamical systems, mathematical systems that do have third order terms, and you have to include them in the model.
Okay.
But a priori, because there's so many, you don't know which ones. So you have to include them all. And that makes a very long list of parameters, and you get then into some numerical problems as well. So this is something that I'm actually very keen to explore, is how do you, this is the Occam's razor problem. How do you choose a model? How do you choose the simplest model, which is as simple as necessary, but not too simple? So I don't actually have an answer to your question, Ali, and I'm interested to have more discussions about this.
Yes, I think that the choice of this dictionary is very important, and also it can influence the sensibility or the identifiability of the parameters too. So, for example, a term with x power 2, the corresponding parameter may be much more sensitive than a term with a linear term. So when we want to put an a priori on the parameters, then choosing, for example, a Gaussian term with the same variance for the parameters may not be very good, and this may explain some of the difficulties of reproducing the time series, for example, later. Yeah. This is one of the points, which is and also it is very important that the different columns of these terms be as much as possible independent from each other.
Yes.
And
yes.
I think that, yeah, I think that the example that you showed, where there was a term of y minus 1, absolute value of y minus 1, absolute value of y plus 1, actually these three terms are dependent.
They're not independent. Yeah.
Yes,
yeah.
And so a priori we are going to assume that these terms are independent. But we know the expressions that we have put, we know that they are dependent. So the choice of the model may be very critical to obtain satisfactory results.
Yes, that's right. No, that's exactly right. And there's some functions where you might just, I talked about these reciprocals of functions. The only hope is to use polynomials, and then you're relying on a Taylor series expansion, because those functions, those strange functions, might not be easily found. But you do see those kinds of functions in biological models. They're quite common. So logistic models. So that's another important point, is how to choose your alphabet. It's a big question.
Yes. Other questions, Lee, if you want to continue, or other people?
Yes. Thank you for the answer. And another question is about the results. For example, in page slide 49, and you show some the result like the
Oh, yes.
yes, at the bottom left, you show the result. I think is the epsilon I 1j minus C 1j
Oh,
minus
yeah. Okay.
1j.
Yeah. Now what I'm doing here, I don't know the true values. So all I've done is I've subtracted values from themselves so that all of these should be on 0, because I want to show these error bars. The error bars are here, but you can't see them. So here we can see the error bars. So I'm not trying to do anything tricky here. I'm just sort of showing the error bars on a common scale. So that's all that is happening there.
So it's a distribution of the posterior distribution of all the parameters, if I understood correctly.
Yeah. So what has been done is we've gone through the Bayesian inference. We've used the map estimate, and so these are the map estimate of these coefficients. But then we've used the posterior, the Gaussian posterior, the covariance of the Gaussian posterior. We've extracted the diagonal terms, which gives us the variances of each of these coefficients. So the square root of those are the standard deviations. So that's what's drawn here.
I didn't quite understand. You said you used the map. So it's
so we've used map.
Yes.
We've used map from, okay, perhaps if I just go a little bit earlier to this discussion here. So this is the analytical solution. So this is how we're finding our estimated values of coefficients, this formula here. And that gives us in this case, it gives us a vector. This is the covariance matrix of the posterior. So we extract the diagonals of this, and that gives us our variances of the psi terms.
So in the model, is that like a hidden variable to estimate?
Yes, I suppose.
Yes.
It's because we've made certain assumptions that the likelihood and the prior are Gaussian, and then we're able to use that analytical solution. If we didn't have that, then we would have to do MCMC or something. We'd have to explore the posterior in order to recover that information. And that would be computationally a much bigger problem. It can be done. So
Okay, thank you. And the last,
thank you.
Last question, maybe a very naive question, is about what is exactly the vulnerability. It's the first time I see this.
Yes. Okay. All right.
What is exactly?
Can I, Nazrin, do you want to talk about this for a minute? So a short definition of groundwater vulnerability.
Yes.
Sorry to put you on the spot. Yeah.
That's
because
okay.
I've been talking with Nazrin about this a lot, so she can answer this.
Okay, thank you.
Yeah, no worries. First, I apologize for my raspy voice. I have a cold, so please bear with me. So yeah, vulnerability. Well, when we have so in our case, when we have pollutants at the surface of ground, and then we have groundwater under, in the aquifers. The vulnerability definition here is the probability of that contaminant going through the soil, the different layers, and reaching the groundwater level and getting it contaminated. So here the term vulnerability is the sensitivity of an area to pollution from the ground surface.
I see, I see. So it means the probability of the polluted water arriving at the underground water layer. If I
Yeah.
okay.
Yeah.
Thank you.
Yeah, the vulnerability in French also it is vulnerabilité, so the same, almost the same word.
I see.
Okay, any questions or remarks?
Thanks, Nazrin.
Yes, Professor. I would like to ask one simple question. For your page 20, I noticed in the table there are two very close form. You call it bilinear term and constraint term. Yes, here, the variance table. So from the mathematical way, I can't quite follow what are the difference between the two for the bilinear form and constraint form. What are the difference?
Yeah,
and the second question is, if we want to use the Bayes approach, how could we use the prior model to give the corresponding form to the bilinear form and also the constraint form? So my two questions about this table. Thank you.
Okay, so well, let me start. So the first, the bilinear form here is we're using a norm, but this is a norm. It's like a norm that you'll see in physics where they have a bilinear product that's defining the norm. So instead of using a dot product type of representation, they've got this bilinear form with the intermediate matrix. And this is important for our Gaussians because our Gaussians that we had later, we have our inverse of the correlation, inverse of the covariance matrix becomes these two, this A and B. So that's why I've distinguished that here. The constraint form is if you have, this particular example, I agree with you. This does look like a constraint that's being applied here. That we've got some value taking away some mean value or something. So that actually looks written a little bit like a constraint. And maybe I shouldn't have done that, but it doesn't matter. In the constrained form, though, in many optimization problems, we have physical constraints. And so we can apply the kind of the Lagrangian method where we maximizing or minimizing a function subject to constraints, and then we've got some Lagrangian multipliers and so on. So that's what's implied here, but I didn't really try and discuss that in any detail.
Okay.
Yeah.
So maybe the constraint term is more general, and one of the application is to use bilinear form to define the regularization part.
Yeah.
So maybe the term is the difference between the two is one for the previous one, the bilinear form, it is more mathematical way definition, and for the constraint one, we can define the physical constraint, use some vector form or some I mean from the physical definition way to give this constraint.
Yeah, no, that's exactly right. I've
you.
spent a lot of time in other work on other types of systems where you have some like flows on networks, you have Kirchhoff constraints, and things like this. So if this was the problem you're trying to solve, then this is a very natural way of implementing that type of constraint.
Okay, I see. Yeah.
So thank you. Yeah.
Yeah, thank you so much. Yeah.
Other questions and comments? If not, Robert, I have still one more question about if you come back to the slide 31 and this difficulty of reproducing
Yes. Yeah.
the time series, and
Mm.
I am intrigued why this happens. Why the time series is very well estimated up to some time, and then after it doesn't follow. Do you think that one of the reason is that we assume that x of t, y of t, and z of t are independent, but we know that they are not independent? Because here we put the equations x, y, z, and the relations, and we didn't account for exactly for the relation between x, y, and z in our model.
Okay.
Probably,
yeah.
probably if I remember that when we were working on this example, we didn't really take care about the fact that we know that x, y, and z are related in some way, and we didn't account for that in the prior laws and in all the different steps of the development of the algorithm. This comes to my mind, but I do not know what do you think about?
Yeah, no, it's a good question. I must admit I haven't thought in that direction, but I know that some people have. So you could establish an inference where you've got x and x dot as your dependent variables, as well as being independent variables.
Yes.
And some people have done that. I should try that and see, but it just seems strange to me to correlate something against itself. So, but that can be done. But I actually suspect the problem is numerical precision. Because of the way these, we have this convergence down to certain values. It's not going down infinitely. We're reaching a machine precision of some form. This is MATLAB, and I should play with this. I agree with you. I should play with this and actually prove to myself and to others that this is the reason for this problem. But it's the same with Cindy. We're reaching some kind of threshold of precision. And I think that is the reason. If we look at these parameters that are in this model, 8 on 3, 8 on 3 in binary is some, and in fact, the others as well, 10 and 28, especially 28, they're not going to be represented very cleanly in a binary representation. And I think it's just the amount of precision that can be stored computationally. I think that's the cause.
Okay.
But I need to check that.
Yeah. Okay.
So, practically speaking, if you wanted to implement this in some, like say you had some kind of real-time system that's making inference, what you need to do, like for example here, if there's some window of time in which the prediction is correct and then it breaks, you need to be measuring measuring the data and trying to make some judgment about when the inference breaks and then re-infer. So there could be the possibility of an algorithm that keeps conducting the inference multiple times in order to make sure that it doesn't break. And such an algorithm, if we did develop such a thing, that would be very robust. And it would be robust to changes. Not everything is the Lorentz system. If you think of vehicles in flight, they're subject to many different conditions, and the conditions will keep changing. And so having some inferometer, if you like, that is continually inferring would actually be a very good way of approaching this problem.
Okay, so
that's my thoughts on that one. So yeah.
Okay. Final call for questions or remarks. If not, Robert, thank you very much, really.
Thank you very much.
Very nice presentation.
Thank you.
And we keep contact. And one of the main objective of this series of seminars is to keep contact after the seminar and to see what are the subjects that we can find for future cooperation. So I think that next time one of my colleagues, Ning Chu and myself, we are coming to Maxent. We can talk again in Maxent.
Great.
But probably in September, we are going to organize September or October. We are going to organize a half day with all the invited speakers that have presented talks in this series of seminars, and then we will discuss all together to future possible cooperations. And thank you again, Robert.
Thank you very much, and
thank you so much.
Please keep me in the notices, so I'll be very interested.
Thank you.
Thank you.
Bye.
Bye.
Thank you very much.
Thank you.